So I'd just like to say a few words. Dr. Mark Miesch is a research scientist at CERES, the Cooperative Institute for Research in Environmental Sciences at the University of Colorado, and the NOAA, which is the National Oceanic and Atmospheric Administration. Dr. Sarah Gibson is a senior solar scientist at the HAO, the High Altitude Observatory at the National Center for Atmospheric Research in Boulder, Colorado. She is also the project scientist for the Punch Small Mission Explorer mission being built by NASA, which is launching in 2025. So please join me in welcoming Dr. Mark Miesch and Dr. Sarah Gibson.
Thank you so much, Fred, and thanks everybody. We really are thrilled to be here. We're as excited as you guys are to see the Northern Lights tonight. Maybe, yes. Mm-hmm. What I'm going to talk about, I'm going to kind of set the scene. Mark's going to give a talk tomorrow, and he'll talk a little bit more specifically about the aurora and what's happening here at the Earth. I'm going to take you back to the source of it all, which is the sun. And I'm going to be talking about the thing that really links the sun and the Earth and auroras and things that happen at the sun, and that is the magnetic field. So I'm going to be talking about magnetism. So there's something about magnetic fields that are really familiar, but at the same time kind of exotic, right? Almost with an element of magic or fantasy, which is maybe why one of the first places you may encounter magnetic fields is in fantasy or in comic books in this particular case. I realized I did one DC and one Marvel, which is incredibly balanced of me. But it could be the hero, there you go, the man who mastered magnetism, the Green Lantern, or it can be the villain, not a hero, Magneto. So let's talk about why we're talking about it here on this tour. And that's because magnetism shows up on the sun. The reason I started out in astrophysics, I actually met Mark, who's also my husband, I don't know if you guys knew that, in graduate school. We were both doing our PhDs in astrophysics. And we both ended up doing solar physics. And for me, the reason was that solar physics is astronomy with a zoom lens, right? I mean, the incredible detail that you can see on the sun. But also because solar physics, the sun, unlike just about any other star, has a very real impact on us here on Earth. And of course, that's why we're all here. Because when you have a storm at the sun, we feel it on the Earth. But let me just kind of set the stage a little bit. We are living in the outer atmosphere of our star, of the sun. There's protons and electrons streaming out in this wind from the sun and hitting us here at the Earth. But do you notice something? Do you see it's being blocked? There's an obstacle. I don't know if you can see that. All those particles are coming along, but they're getting deflected. Guess what is deflecting all this stuff coming from the sun? Who can guess? I'm going to give you guys a really big hint. Every time I ask an open question like that, the answer will be magnetism. So, guess what's blocking? Yeah. In this case, it's the Earth's magnetic field. Let's go back to the sun. And, what's causing all this? What's driving it? Where's this magnetic field coming from? Well, there's different models. This is one of my favorites. I don't know if you're familiar with this particular cartoon. We've got the guy who lives inside the sun, and his job is to rise and set it every day. And, of course, it's very hot. So that's, viable, but doesn't really help us. So how do you think we see inside the sun? Does anybody have any guesses? Oh, and actually, it's not magnetic field. It's not the right answer. Sorry. There's one exception to my rule. So tell me something. If you had a fire right there, you're warming your hands in front of the fire, and you start to walk away from the fire, you're going to get colder or hotter as you leave the fire?
Colder.
Colder. So how is it that the surface of the sun is 5,600, but when you start to get out into the atmosphere, it jumps to 1,000,000 degrees?
Magic.
Very good. Magnetism. You're exactly right. It's magnetism. That's because stuff is escaping. And it's called a coronal hole. And when you have a coronal hole, it means that the magnetic field is open out into the heliosphere, and it can actually stuff can come out to us here on Earth. But this stuff here, which we call closed magnetic field, I'll make this run one more time. It's brighter. It's where you see a lot of loops and so on. It doesn't kind of continuously stream out. But that's where you get the storms, because the magnetic fields get super twisted up and they snap and they release energy. And that's what drives one of those big blobs, which are called coronal mass ejections. So here we're going to see a movie. This is a coronal mass ejection. This is the sun. Sort of inside here. It's been occulted by a chronograph. And you can see that when the magnetic fields get twisted up and energized enough, they hurl stuff out through the solar wind. Okay. And this is now the sun in the middle, and it's showing you both. It's showing you all that stuff that's sort of streaming out all the time, and then the big blobs that happens when you have a coronal mass ejection. So you have storms in the wind. And so this is called a co-rotating interaction region. It's called co-rotating because you can also think of it like a lighthouse. So here's one of those coronal holes, and the sun's rotating. It sends it out to you, spiraling around. 27 days later, when the sun is rotated, it sends it out to you again. So you can actually predict one of these space weather effective things like a month in advance, because if it sticks around, and they do tend to stick around for a few months. So there's two kinds of space weather that can drive auroras. You can have the coronal mass ejection, where you get this twisted magnetic field racing through the interplanetary medium and the solar wind, getting here 2 or 3 days later. Or you could have this kind of pattern in the solar wind, where you have this sort of fast wind that's coming around, and you can have more than one of them. One coronal hole here, one coronal hole here. So you go whoosh, you got a fast wind, whoosh, you got another one. And so every week or two, you might get another space weather, another auroral event. All right, this is the last chapter, chapter 5.
And actually, before you go on, if
Sure.
you go back,
Yeah?
that's what's happening today.
Which one, the CME or the
Both
CII?
of them. Both of them. So that on Sunday there was a X-class flare from a region that like Sarah was talking about, that flares and CMEs often go together, but flare, it takes 8 minutes to get there. So Sunday that happened. The CME is going to hit today, but it's combined with a high-speed stream from that coronal hole that happened, that rotated around from 27 days ago, and it's coming back.
So it got a kick in the pants, and it went.
So yeah, so we have kind of a combination of both today.
Yes. And
So
I'm
the
gonna
sun is rotating 27, it takes 27 days to rotate the sun.
Yeah.
Once.
on
That's it.
average, yeah.
That's slow, isn't it?
Yeah, it's all sorts of questions about, if there are stars. So, for example, there are stars that are going, young stars, they're going much, much faster. And guess what? When they're going much, much faster, that's also associated with much stronger magnetic fields. And you get these crazy stellar flares that are 1,000 times more energetic than the Earth gets. So, you might say it's slow, but you might say it's just right. Because, there's one of the things with exoplanets, right? People are realizing that it's important to be in what they call the Goldilocks zones of not too close to the star, not too far from the star, sort of like the Earth is. But also, if you're with a star that has a lot of this kind of space weather, and if you have like really severe space weather, it's going to rip the atmosphere right off of your planets. So you have to pay attention to this, and the sun's rotation speed matters for that. So you want to look for a star, if you're looking for life, that's maybe also kind of like the sun and the way it behaves in space weather. It's like all the plots from 1750 on, and just this little blue piece from 1950 is what I plotted here. And you can see there's not very many sunspots, there's lots of sunspots, not very many Tunican. It's kind of a lame, not a very big cycle there. And anyway, coming up, but look at this one. And, dun-dun-dun, you are there.
But for tonight, I wanted to talk about what we saw last night. And so I wanted to ask, what if you knew nothing about science? What if you knew nothing about the Northern Lights and you saw that up in the sky? What would you think? How would you attempt to explain what you're seeing? And so this is a journey that humanity has had. It's taken us centuries to sort of make any headway on that question of what we're seeing when we look up to the Northern Lights. But another big thing to happen in the 18th century, there's a guy named Celsius that you've probably heard of. But so he said that aurora are linked to the Earth's magnetic field. And so this is usually credited to Celsius, but this is how his student
Olaf Hjorter describes it. He says, "Who could have thought that the northern lights would have a connection and a sympathy with the magnet? The first time I saw an aurora to the south and noted simultaneously a great movement of the magnetic needle was in March 1741 in the evening. When I announced this to the professor, he said that he had noticed such a disturbance of the needle in similar circumstances, but had not wished to mention it in order to see whether I too would light on the same speculation." Management. Yeah, so the relationship between students and advisors unfortunately hasn't changed much. Like Sarah told me yesterday, so that our understanding of what causes the aurora now starts with the solar wind. So this is a real image from the NASA's stereo spacecraft. And these are, like Sarah was talking about yesterday, it's a coronagraph, so it's a simulated eclipse. You block out the disk of the sun so that you can see the solar wind around it. And just a rule of thumb, that the corona is about 1,000,000 times dimmer than the disk of the sun. So even if 1% of the disk of the sun is showing, it's enough to drown out the corona and the glare. So if you've seen, if somebody says, if you ask somebody, did you see the total solar eclipse of 2024? And they said, yeah, it was 99% covered up, where I was, no, they didn't see an eclipse. Because it has to be 100% for you to see the corona. Okay, so during magnetic storms, so we talked about, and I said that we're interested here mainly in the electrons. The protons come down too, but they're not moving fast enough to cause the light we see with our eyes as aurora. So the electrons come streaming down the magnetic field lines and they hit the Earth in sort of an oval pattern, because that's the way the dipole magnetic field is sort of aligned. And they come and they whack into the atmosphere. And so that's why you get an oval. And so the layers of the atmosphere, the bottom layer where we live is called the troposphere. That's where the weather happens. The stratosphere is where airplanes fly. And then there's something called the mesosphere. There's the Kármán line, which some people define as the edge of space. Aurora happen up here in what's called the thermosphere. So this is not far below where the space shuttle is. So this is about 100 kilometers up to about 150 kilometers up. That's where aurora occur. International Space Station is a little above that, and then satellites are up in what's called the exosphere. This focuses on the two most important atoms, molecules, at auroral heights, and that's molecular oxygen, atomic oxygen, O, and nitrogen. So if you see up at the highest levels, I said about 250 kilometers is the highest aurora. Up there, it's mostly oxygen. But down at 100 kilometers, down here, if you get particles going down toward, they're energetic enough to get down to 100 kilometers, they have mostly more nitrogen down here. It's more numerous than the oxygen.
Does that count for the colour variation? You were saying that the sort of reddish, pinky colours was higher than the greenish.
There you go.
Oh, okay.
Mark, you're so good at this.
All right, so this is the atomic oxygen. This is what oxygen looks like, and the color that we saw most last night was the red line. Red light from oxygen is the highest. It has that blood red color. Then the oxygen at lower, about 100 to 150 kilometers, gives you the green, and then the lowest level gives you sort of the violets and the reds. All right, and these are some of the forms that aurora can take. So you can have, we certainly saw rays last night, we saw coronae. That's when you're sort of right below it, and you're sort of right below the rays, and they all seem to come from the same point. You can have these bands and arcs that stretch across the sky. So Sarah and I in Iceland in January, we saw this beautiful arc that went from horizon to horizon. And then you can get patchy aurora.
Did we see pretty much everything last night? It feels like
Maybe so,
Yes,
yeah.
yes.
Very familiar.
Yeah. And so the extent of a lot of people have been looking at our Space Weather Prediction Center website, which has the predictions from something called the Ovation Model. And as you know, the extent of the auroral oval depends on this sort of magnetic activity. So as measured by sort of the KP index. So if you have a small, like a KP of 3, then it's only these latitudes, but no, it still includes us. If you have a bigger, like a KP of 9, then that goes to the sort of the extends to the US. But again, where we are right now is part of that.